Right, you should have your notes for lecture 18, random variables. All right, definition, a random variable, hereafter just RV for random variable. X is a variable. It is a variable whose values are determined by the outcomes of a random experiment. So it's a random experiment, it's a random variable. All right, immediately we need to get to the probability distribution of the random variable x. And of course you need to pause and fill all this in, right? The probability distribution of the random variable x is the pairing of each value of x with a number such that it is possible to compute probabilities associated with x. And that's maybe a little complicated sentence. The examples we do will make it real simple. In fact, we're going to go right to an example. This is the example where we toss a die and we notice the number facing up. Only now, instead of thinking those numbers as being outcomes in a sample space, we're just going to think of them as values of a random variable. It's just a little shift in thinking, not really very much. So we toss a fair die, and x is the number facing up. X has the possible values 1, 2, 3, 4, 5, 6. The probability distribution for x is simple. It's just a chart that gives each value of x with corresponding probability. Typically, we've been drawing our charts vertically, but I think I drew this one horizontally. So notice I have over here, x is the value of the random variable, and it can take on the values 1, 2, all the way up to 6. And correspondingly, the probability of each value of x is 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6, because we compute that by counting up how many ways can you get, say, a 3, 1 out of the total number of possible ways, 6, and they're equally likely, so the probability is 1/6. That's just our classical probability formula. All right, and I guess I want to say here that how do we compute the probabilities for x? Well, I just basically told you. It's not as stupid a question as it seems, because we've already done it, but like I said, we're kind of shifting our thinking now and thinking of values of a random variable. We have to backtrack to the event that corresponds to a particular value. And here, it's real obvious. If x is 3, that just means the die came up 3, so the probability is 1/6. And we'll get a little bit more complicated in the next example, and then even more so in the example in the next lecture. But the above chart should look similar to a relative frequency chart. Like I said, I drew it horizontally, but if you drew it vertically, it'd look more like a relative frequency chart. And what you have is the random variable values in one row, and the other row has the various probabilities, which kind of maybe start to make you think of relative frequencies a little bit. There is a connection, as I've already been saying to you. But right now, why don't you draw the probability histogram? So you draw it the same way you draw a relative frequency histogram for a discrete set of data. You have just 6 possible values. You draw your histogram bars and center them appropriately and give them the right height. So why don't you pause me and try that, and then I'll do it. Okay, here's what you should have, something that looks like this, right? Kind of boring. The bar is centered, the first bar is centered above 1, and the next one above 2, et cetera, all the way up to 6, and each one has probability or height 1/6. Again, you notice that if you think in terms of area, the area, let me get down right about here, area of each bar is the probability, right, which is 1/6, because it's 1/6 times 1. The width of each bar is 1, and the height of each bar is 1/6. So we come back to this idea of area being probability. It's not always going to be true in histograms, as we've already seen when we dealt with relative frequency, but it's true for most of the things that we set up here. And if we start thinking that way, as I've already indicated, it's going to help us a lot in the future. Okay, well, I think I will give you just one more quick example then, so let me rub this out. And let me get rid of all that. And we'll do the example that we've already done. That's just a little more complicated, though. So the experiment, so this is an example. the experiment, if you want to think of it as an experiment, couple has three children. Let's let X equal the number of girls. Okay, so the possible values for X are, well, you can have no girls, 1, 2, or all 3 can be girls. All right. But what's our sample space? What we're looking for in order to compute probabilities, we're looking for a sample space of equally likely outcomes. And we saw before that that's the sample space, excuse me, where we have girl, 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 boy, girl, boy, girl, girl, boy, 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 girl, girl, boy, girl, boy, 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 girl, and boy, boy, boy. Okay, so that's very different from the set of possible values of the random variable X, right? But now what I want to do is build the probability distribution chart. So I will have here X and P of X. Really, what I should do is I should make, when I write a random variable, it's just a very common convention to use a capital letter X, or a capital letter, and usually we use capital X. But when we talk about the different values of X, we usually use a lowercase letter. That's what I should have done on the first chart. I don't think I did that. Then on this chart, I will put the probability of X being that value, so I can write that like this. Okay, I didn't do that on the first chart I had up. I just had probability of X. But this means the probability of X equaling these various values. They are 0, 1, 2, 3. Okay, what's the probability then that X equals 0? The answer is I have to come over to my sample space and figure out the event that means X equals 0. And for X equals 0, since X is the number of girls, I get just this one, right? So the probability that X is equal to 0, we can write that as P of 0, really just to abbreviate it. That's 1/8, isn't it? What's the probability that X is 1? Let me go to green for that. The probability that X is 1, what's the event that that corresponds to? I have to go through and find where the number of girls is exactly 1. No, no, no. Here's 1. No, here's 1. Here's 1. And that's it. There are 3 possibilities out of 8 equally likely. So the probability of 1 is 3/8. I might as well shift to pink. What's the probability that X equals 2? That corresponds to the event, since X is number of girls, it corresponds to the event where each outcome in the event in the subset has 2 G's and just 1 B. So that's no, here it is, and here it is, right? 2 girls and 1 boy. Again, that's 3/8. So the probability that X is 2 is 3/8. Okay, to figure the very last one, I could look at this and say, I have taken care of all other possibilities except that one, and I've so far gotten 1/8 and 3/8 and 3/8. That totals up to 7/8. So I already know my last answer. What color should I use? Can I use this one yet? I already know what my last answer is going to be. It has to be 1/8. Because it's the complement of all the rest of these, which have a total probability of 7/8. But I can see the one that I haven't gotten yet is all 3 girls is right there, and indeed it's 1/8. If we draw the probability chart for this, we have here is 0, here's 1, here's 2, and here's 3. So I'll go up. That's 1/8. And then I got to go up for 1 and 2. I got to go up 3/8. So 1, 2, 3. So it'll be like that. And it'll go all the way across right to there, won't it? And there's a bar up the middle, right? And then lastly, I got to go back down to 1/8. So the probability of the area here is, this is 1 wide and 1/8 tall. So the probability is 0. girls is 1/8. Probability of one girl is 1 by 3/8. I didn't put that in, that's 3/8. And so that's 3/8. Probability 2, the area there is 3/8. Probability of 3 girls, the area there is 1/8. All right, next lecture we'll do an even more